All right, we've made it this far. We might as well go the rest of the way through this look at Taylor series. Today we talk about the convergence of Taylor series. In other words, if we stop writing a series at some point, how close do we get to the actual retail price? If we cut off a series and make it a polynomial, how close is that polynomial? So let's talk a little bit about Taylor's formula. And Taylor's formula, well, let's set it up. Let's suppose that f has derivatives of all orders, which means that you can always take the next derivative in an open interval. Call that interval I, containing A. A is the center. Then, for all positive integers n and each x in the interval, f of x is. And then what's gonna pop up here, and what popped up in your text looks a heck of a lot like the thing we did with Taylor series. F of a, f prime of a times x minus a, f double prime of a over 2 factorial x minus a squared, and then it goes for a while, right? But Taylor's formula depends on us cutting short a series, and this is where we cut it short. We take the nth derivative at a over n factorial times x minus a to the n. That's the last term we write. F of x is all of this plus a remainder term. And that remainder term is different for every value of n, so we call it r sub n of x, where r sub n of x is the n plus 1th derivative at some point c over n plus 1 factorial times x minus a to the n plus 1. So this, oh, whoa, this is the remainder term. It is sometimes referred to as the Lagrange error bound, mostly because Lagrange studied it. If this remainder goes to 0 as n goes to infinity, then the more terms we add, the smaller the remainder, and we can say that the Taylor series converges to f of x for all x. Let's demonstrate. Find the quadratic polynomial that approximates f of x equals the square root of x near a equals 4. Use it to approximate f of 5, bound the error. So there's several things to do here. One is to find the quadratic polynomial. So to find a quadratic polynomial, we need derivatives of square root of x. The first derivative is 1/2 x to the negative 1/2, and then the second derivative is negative 1/4 x to the negative 3/2, and then the third derivative is 3/8 x to the negative 5/2, and so on. We only need through here to make the quadratic polynomial, but we're going to have to bound error, and error is based on the next derivative, so I took 3 derivatives. then we're supposed to figure out what f of 4 is, and what f prime of 4 is, and what f double prime of 4 is, and what f triple prime of 4 is, because we're going to need that. And those numbers are pretty easy to get. This is 2, this is 1/4, this is negative 1/32. I guess we don't really need that to make a quadratic polynomial, do we? So f of x is approximately f of a plus f prime of a times x minus a plus f double prime over 2 factorial x minus a squared. So when we try to approximate f of 5, f of 5 is approximately 2 plus a quarter of 1 minus 1/64 of 1 squared, right? 5 minus 4, 5 minus 4, right? This is approximately 2.23438. So let's bound the error. The error, the absolute value of the error, is less than or equal to the n plus 1th derivative at some point c between 4 and 5 over n plus 1 factorial times x minus a to the n plus 1. Now in our case, we stopped at n equals 2, so n plus 1 factorial is 3 factorial, and n plus 1, n plus 1 is 3, and we know what the x is, right? X is 5, so 5 minus 4 is 1. So the question is, what's the biggest this can be between the center and the place we care about? What's the biggest that this can be between the center and what we care about? Well, it turns out that that happens when x is 4, and it happens that when x is 4, this fraction is 3/8 times 1 over 32, and that's over 6 times 1, and that's approximately 1 over 512. So what does that mean? That means that this approximation that we found is no more than that away from the actual square root of 5. So what's important to remember here? The Lagrange error bound is the next derivative anywhere between the center and the place we care about, n plus 1 factorial, x minus center to the n plus 1. We know what this is because it's given. We know what this is because it's given. We figure out what the maximum for this is on the interval from the center to the place we care about, and then it gives us an error bound. I'll do a couple more examples in a separate video, but if this does it for you, then great. See you soon.